All right, we have just finished up substitution reactions. We looked at what was necessary, what were the conditions for SN1 versus SN2. Today we're going to start with the next chapter, Elimination Reactions, Chapter 8. And today we'll be teaching elimination reactions to this little Fisher-Price guy right here. All right, so a little background first. In elimination reactions, as we recall from previous chapters, we're going to be forming a double bond, a carbon-carbon double bond. In order to do this, we're going to need a molecule such as CH3, CH2, CH2 here, drawn out real fancy, with another carbon with a halogen on it, a leaving group on it. And we'll need a base, such as potassium tert-butoxide. It will come in, the base will come in, form a bond with this hydrogen, taking this hydrogen off the carbon. The sigma bond pair will become a pi bond between the two carbons. So in this reaction here, the potassium tert-butoxide will come in, take this hydrogen, the bonding pairs, sigma bonding pairs, become a bonding pair between these two carbons. The leaving group bromide will leave. And we end up with, if we can see where they come from here, CH3, CH2, CH, because one hydrogen is missing, double bonded to this carbon that now has its two hydrogens on it, and the bromine leaving group is gone. Because a hydrogen and a bromine left, bromine being a halogen, this type of reaction is called a dehydrohalogenation reaction, an example of elimination. Note also, in order to get the elimination, you have to have a carbon with this leaving group on it, in this case the halogen. The carbon next door, one of the carbons next door, must have a hydrogen on it. The base must take the hydrogen from a carbon next door to the carbon that contains the halogen. We're going to call the carbon that contains the leaving group the alpha carbon, and we'll call the carbon that has the hydrogen on it the beta carbon. So the base will always take the proton from the beta carbon. For that reason, we usually call this beta elimination or beta hydrogen elimination. The bases that can be used are our standard bases, sodium hydroxide, potassium hydroxide, also our alkoxides, sodium methoxide, sodium ethoxide, and as we saw from above, potassium tert-butoxide. All right. So, to get a better understanding of what's going on here, let's take a look at the alkenes that we will get as a product of these reactions. Recall, double bond, we've got a sigma bond and a pi bond from the unhybridized P's on these sp2 hybridized carbons. In terms of stability, what we find is if we have a carbon-carbon double bond, one carbon has two hydrogens on it, the maximum it can have if it's double bonded. The other carbon has one hydrogen on it and an R group. This is mono-substituted. This is going to be the least stable of our alkenes. We have a number of orientations when we have two R groups on the double bond. We can have two R groups on the same carbon, a geminal disubstituted double bond. We can have the two R groups on different carbons but opposite each other, trans disubstituted, as we've seen before. We have the cis isomer that we've seen before. We could have, if we had three R groups on here and one hydrogen, one of these is supposed to be a hydrogen, then that's a tri-substituted double bond, and four R groups is a tetrasubstituted double bond, and tetrasubstituted is the most stable of these. Okay. Now, an interesting thing happens when we look at geminal versus trans versus cis disubstituted. Trans, due to steric hindrance mainly, is going to be more stable than our cis disubstituted double bonds because we can have some steric hindrance between these two R groups. Geminal versus cis, there are some compounds where geminal is the more stable compared to the cis, others where the cis might be more stable, so geminal and cis have about the same stability. Recall also, pi bonds cannot rotate, so we cannot rotate these from one side to the other. So if you do have the trans double bond or the cis double bond or the geminal double bond, these are diastereomers. Except actually geminal would not be diastereomers because recall diastereomers, stereoisomers, have same connectivity, different orientation in space. Geminal would have different connectivity. If the CH3 was over here, that would be different connectivity. So the geminal isomer is not a diastereomer of the cis and the trans. All right, going on to the next page. Let us look at the mechanisms for substitution. You will be happy to know that there are two mechanisms. The first one we are going to look at is the E2 mechanism. What does E2 stand for? Well, as you probably guessed, E stands for elimination. And if you remember SN2, substitution nucleophilic bimolecular, E2, elimination bimolecular. It is second order, two reactants in the rate determining step. Our standard example here of the E2 mechanism, if we have our molecule here, CH3, carbon with a halogen on it, another CH3, and a methyl over here. This methyl drawn out all fancy like with the 3 hydrogens on there because I want to emphasize that this base is going to come in and take one of those hydrogens. The carbon hydrogen bond breaks, the 2 electrons of the sigma bond become the pi bond between the 2 carbons. Note this carbon has the leaving group on it, which leaves, that's the alpha carbon. The base attacks the beta hydrogen, and so we're going to end up with a double bond between these two, one hydrogen gone, the bromine gone, double bond between those 2 carbons, and here is our alkene that we get from here. Note the base hydroxide took a hydrogen, becomes water, and we've got the bromide. This is the E2 mechanism. It is one step, all of this happening at the same time, which means if we look at the transition state, as the base attacks that hydrogen and the oxygen-hydrogen bond forms, the carbon-hydrogen bond is breaking at the same time. The carbon-carbon double bond is forming and the carbon-bromine bond is breaking. All that happening at the same time. And as we remember from our mechanisms, if we're looking at the rate law for this reaction, because it's one step, it is the rate determining step, the rate will equal K, rate constant, times the concentration of the substrate, our alkyl halide, times the concentration of our base. Now, what types of things make E2 reactions run better? Well, strong bases. The stronger the base, the faster the E2 reaction, because the base is in the rate law. Better leaving groups. As we saw before in the substitution chapter, poor leaving groups are not going to get a reaction. Polar aprotic solvents. Recall acetone, dimethylformamide, tetrahydrofuran, acetonitrile, the common aprotic solvents. All right, something to mention here, we'll get into a little bit more. Here's 2 bases that we haven't discussed too much, DBN and DBU. These are also strong bases and they work very nicely for E2 elimination reactions. All right, well, what type of substrates do we want with these E2 elimination reactions? All right. It turns out primary substrates do not like to do E2 elimination. The best substrate, the best alkyl halide will be a tertiary substrate. Tertiary substrates, fast elimination reactions via the E2 mechanism. And as usual, secondary substrates, meh, they don't care. Recall this is the opposite of our SN2 mechanism. SN2 primary would be the fastest and tertiary would be the slowest. All right. So what happens though if you can get multiple products when you do your elimination? Let's look at this reaction right here. We have butane, or excuse me, 2-butyl-bromide, or 2-bromobutane here. And here's our alpha carbon. It's got the bromine on it. We know we're gonna, if we add a base, we're gonna add tert butoxide here as our base. It can attack a beta hydrogen. Well, where are the beta hydrogens? Well, here's the carbon next door. There's 2 beta hydrogens there. Here is the methyl next door this way. 3 beta hydrogens there. So the question is, which hydrogens on which beta carbon will the tert butoxide attack? The methyl or the methylene here? Turns out it'll do both. Some of the tert butoxides are going to run into a hydrogen on the methyl, take one of those hydrogens, put the double bond between those 2 carbons, and we have our double bond here. Nope, this is a CH2. All right. However, sometimes the tert butoxide will take one of these hydrogens and we'll get the double bond over here. Wouldn't it be nice if there was some rule that we can follow that will tell us, okay, which one of these do we get more of? Well, good news. There is a rule, the Zaitsev rule. Zaitsev found when running these reactions multiple times that the major product, you do get both products, but the major product has the more substituted double bond. So this product here, when the base attacked one of these beta hydrogens of the CH2, gave us a more substituted double bond. As we remember, more substituted double bonds, more substituted are more stable. Therefore, we have a more stable product, we get more of it. The less stable product, we do not get as much of that. All right. By the way, Zaitsev's rule, I've heard it pronounced Zaitsev, 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 all sorts of different names for that. And then a little while ago, I was watching some hockey, and the announcers for the hockey game, the Toronto Maple Leafs were playing, and they have a player named Zaitsev. The hockey guys pronounced it Zaitsev. If anyone knows how to pronounce Russian names who doesn't happen to be Russian, it would be a hockey announcer. Therefore, I'm going with Zaitsev for the name of this rule. All right, let's turn the page, see what's next. Okay, so let's look at this problem right here. You have a methyl cyclohexane with an iodine on the same carbon as the methyl group. You attack it with the base hydroxide. And question, what is the product going to be, or what are the products going to be? You could pause right here if you want to try it for yourself. But how do we go about answering this problem? First thing, all right, I'll tell you at this point that we're going to be running the E2 mechanism, which means we're going to do elimination. Recall, it's always beta hydrogen elimination. So first thing, find the alpha carbon. The alpha carbon is the one with the halogen. We've got the iodine there, so here is the alpha carbon. The alpha carbon contains the iodine and the methyl group. So the question then, and where are the beta carbons that have hydrogens on them? Well, as we can see, we've got a beta hydrogen right here, a beta carbon with hydrogens here, and the methyl, that's beta. It is one next door to that alpha. So what products will we get? Well, first thing to note that going around the ring in this direction is the same as going around the ring in that direction, therefore these two carbons are equivalent. So if we take one of the hydrogens from the CH2 here, it'd be the same, we'll get the same product as taking a hydrogen from this CH2 up here. So that can happen. We can take one of these hydrogens off this CH2, form a double bond here. Note the methyl group will stay. We also have this methyl as beta, so we could take one of the methyl hydrogens and form a double bond here. So when we look at it, there are our two products. We form the double bond here by taking this beta hydrogen, or we form the double bond here. Now, which do you think is the major product, which is the minor product? What would Zaitsev say? Well, Zaitsev would say that this would be the major product because this is a 1, 2, 3, a tri-substituted double bond, only one hydrogen right here, whereas this is a di-substituted double bond, R groups here and here, two hydrogens there, so Zaitsev says this will be the major product. Ah, I was right. Well, makes sense, there are my notes. All right, but note, because the major product can be predicted, because we know the region where the double bond will be, because we knew it would be, the major product would have the double bond inside the ring versus outside the ring, we call these regioselective reactions. We mainly get one major product and we can predict the region in the molecule, the place where the double bond will be. All right. Now, when we look at this reaction, if we have a benzene ring, a CH2, a CHBr, and another benzene ring, we add strong base, we're going to get E2 elimination. Note, one of these hydrogens will be taken, the bromine will go, the double bond will form between these two right here, and note we can get the trans and the cis product. Zaitsev tells us that the major product will be the trans product because it is more stable than the cis product. Because we know that, we can say these are stereoselective. This reaction is also stereoselective because we've got the trans stereoisomer in greater abundance than the cis stereoisomer. Okay, so here's a couple for you to try. If you've probably already looked at them. Add our strong base, our alkoxide here, ethoxide, and note we have a beta carbon here with hydrogens on it, beta carbon here with hydrogen, so we could get a double bond here or a double bond here. We will get both. Note that this is the major product since it is tri-substituted. This is the minor product since it is di-substituted. What will happen when we run this reaction? Well, here is our alpha carbon containing the chlorine. Note we've got two hydrogens on this beta carbon here. Note no hydrogens on this beta carbon here, which means we cannot get in a double bond right here. There's no hydrogen beta over here to eliminate. Therefore, we will only get the product with the double bond right there. All right, and that is the E2 mechanism. Note there is another mechanism for these reactions, the E1 mechanism. Elimination, one unimolecular, which means only one reactant in the rate determining step. This is a two-step reaction. The way this one works is you have your substrate. Here is your alkyl halide. And the first thing that happens is the leaving group leaves. Leaving group just up and leaves, leaving a carbocation. We recall that the carbocations are not very stable, and this reaction is a slow reaction to generate this carbocation because the activation energy is pretty high. Now, once you have the carbocation, you can have a base a weak base, such as water, come in, and it can snag the beta hydrogen. Note, this carbon, the carbocation carbon, used to contain the iodide. It is the alpha carbon. This carbon here is now the beta carbon, so it has a hydrogen on it. The base can take that hydrogen. We will form a double bond between those two carbons and get this product here. Because the slow step is the first step with just the leaving group leaving, the rate law is rate equals K times the concentration of our substrate. All right, let's turn the page. And look at the conditions for E1. All right, as we see when we look at the substrate, tertiary substrates have the fastest rate. Primary substrates are very slow. That is to be expected because if we had a primary substrate, we'd have to have we would generate as an intermediate a primary carbocation. And we know from our Hammond postulate that the transition state is going to look a lot like the carbocation. Therefore, we know, since we know that primary carbocations are unstable, they're less stable than secondary, less stable than tertiary carbocations, we know that the transition state will also be higher in energy due to the Hammond postulate. All right. Note that the base is not in the rate law for this reaction because the slow step is that first step with just the base, or with the leaving group leaving. So this reaction is favored by weaker bases. Recall E2 liked strong bases such as hydroxide or alkoxides. E1 prefers weak base such as water or alcohols. Also note Zaitsev rule applies. So if we have this tertiary alkyl halide with water, the first step is the leaving group bromide will leave, giving us a tertiary carbocation here. Water can come in. This is our alpha carbon. Water will come in and attack a beta carbon hydrogen down here or up here. Same thing, or one of the methyl hydrogens to give us these two products. Zaitsev rule applies. This more substituted double bond will be the major product. All right. Now, it's been a while, but if you recall with SN1 mechanism, recall the first step of the SN1 mechanism is the leaving group leaves giving a carbocation. Recall that SN1 mechanism prefers tertiary substrates. All right. So then what's the deal with SN1 versus E1 when they both have the same first reaction? A tertiary substrate is our starting material. The leaving group leaves giving a tertiary carbocation. All right. Well, recall that SN1 reactions are favored by tertiary alkyl halides, weak nucleophiles, which are weak bases, and polar protic solvents. E1 is also favored by tertiary alkyl halides, weak bases, weak nucleophiles, and polar protic solvents. So then, if we run this reaction here, have a tertiary alkyl bromide, add water, a weak base, a weak nucleophile, and its polar protic, what are we going to get? Substitution or elimination? The answer is both. Every time you set up SN1 reactions, those are the same conditions for E1. Anytime you set up an E1 reaction, that's the same conditions for SN1. You will get both products. Yeah, Fisher-Price guy finds that insanely interesting. Yeah, we will get the elimination, the E1 elimination product here, work through the mechanism. We will get the substitution mechanism here. Recall the water will attack the carbocation for substitution. And every time our product has an oxygen or nitrogen that is positively charged and has hydrogens on it, a deprotonation reaction will occur. Some extra water will come in, snag that hydrogen, and we will get the alcohol. All right, so those are the two mechanisms for this reaction. And we will continue on with the next video. I want to keep these a little bit short, so the next video we will start looking at stereochemistry of E2 and then start looking at, okay, what other things do we need to worry about if we're dealing with SN1 versus SN2, E1, E2? How do we know what's going to happen?